small room, I can speak up. But the main thing is we have to record this. That's why we need this microphone to be on. I hope you all understand this. So please don't lose your patience, but you will get back. When we are not recording right now. Are we recording? But more wait until everything starts. So in the meantime, just for this class, I wanted to ask you. So you said majority of you raised your hand on your basic knowledge about climate change, which is impressive. I want to ask a follow-up question on that. How many of you have used climate data, climate change data? For example, climate models, CMIP 5 or CMIP 6? Raise your hand, please. I see 5 or 6 of you have used. CMIP 5 or okay. CMIP 5 or CPs you've used. Okay. CMIP 6, anybody has used? CMIP 6 is a climate model data that we are talking about. Have you heard of the term CMIP 6? Yes. And have you not used it? Right? We have not used ISO. Okay. You have? No. So anyway, I'm going to be talking about the basics. I wanted to know how deep I should go in terms of the basics. That's the reason I'm asking this basic question. I think we used our time to understand your background, so that's important. But of course, I will get to know more about you individually because 5 days will go very quick, and the material that we have to cover um, a lot. There is plenty of material that I need to cover in the morning, and then followed by the hands-on session for 3 days. Day 1 today, day 2 tomorrow, and then day 3, like Dr. Pramada Madam talked about. Day 3 we will have a field visit to a local center, and then day 4 we will have the third hands-on session, and day 5 we will finish the last day. During the break time, you can interact with me and Dr. Pramada Madam for relating to what you are planning to do or how it might help if we modify some things that will be directly related to you. So with that basic introduction, I'm going to actually jump into my slides. It'll be an hour-long presentation just on the introduction side. So just to break the monotony, I will come to the floor. I will ask you some questions if you don't mind, or if you have some burning questions, you can even raise your hands during my presentation. We'll have a break and then continue this conversation. Again, with the assumption that some of you are familiar with the topic, but some of you are not, I have to still go with some of the introductory material. So please bear with me on that. Okay, so for example, when I'm talking about introduction to climate change, of course, we need to understand what are the learning goals of each of the sessions that we have. So I put this slide here. The main thing is to understand what are the drivers of climate change, what are the evidence of human-induced or human-caused climate change, describing how warming alters the energy balance and hydrologic cycle, identify global and regional trends in heat, rain, floods, and droughts, explain the difference, primary difference between two generation of climate model products, SSP or socio-economic pathways, and then RCPs, representative concentration pathway scenarios, two different types of climate model outputs, and then what kind of uncertainties they have in those, and then recognizing the linkage between hydrology. We mostly come from hydrology background with minimum understanding on atmospheric science or climate science, but then we want to tap some of these explicit linkages between hydrology and climate, and then how they are manifesting into climate extremes and what kinds of risks that we have. So those are the learning objectives. I will come back to this graphic later, but this is squeezed here. What we are talking about is basic thing about climate change. We all know that climate change is happening and the change is really fast and rapid. And it will continue to change over time. Even, let's say, if things change as of today in terms of fossil fuel emissions, industrial pollutions, and things like that, even the change that what we are seeing today in the climate system will continue to evolve for the next 50, 70, 80 years. So the change that we have introduced already is happening, 40, 50 years of industrial era, and now the change will also continue to happen. And now we also need to identify, are these natural? The changes are natural, or is that human induced change that we are looking at in the climate system? So what are the activities that are causing climate change that we introduced into the system? So those are the things that we want to be talking about. And then if you look at the graphics here, I will again show the full, expanded or blown up picture. 30-year average of temperature increase or change in temperature, that what you see here, more red planet that we see, and compared to the last 124 years or so, the change was mild compared to the last 30 years of change, dramatic increase in temperature, particularly over the Arctic region. I will come back to this slide or this graphic again, but I just wanted to show you that this is one of the change. When I'm talking about climate change, it may be abstract for many of us. What we want to understand is the temperature is changing from the past conditions. That is one thing. And then all the other variables are also changing. For instance, of course, planet Earth in a position, Goldilocks position, what we call, is exposed in the planetary system with an angle tilted towards this side, facing the sun. You can see the radiation that's coming and hitting the planet. Basically, low intensity or low density of incident rays on the northern side causing winter, and more high density incident rays on the south side, which is causing warmer conditions, that is the summertime. When the south pole is warming up, the north is cold, and the north is warming up, the south is cold. That is the scenario that we normally see because of the position of the planet Earth and the way how it revolves around the sun. And now what you are seeing here, this is really basic stuff that we need to understand. Of course, what we are looking at is the solar radiance, right? Over the last 140 years or 100, roughly about 140 years. There will be some fluctuations because of a lot of other uncertainties or solar activities. But you can see the radiance more or less remaining the same coming from the sun. But look at the temperature profile here. It is steadily increasing. When we are talking about the radiance which is coming from the sun is a constant source of energy that is remaining constant, but the temperature is showing some increasing trend here. And we wanted to understand, as scientists, we want to understand why that increasing trend that we are seeing here. And the bottom line here is that sun is the ultimate source of energy, and that we want to really see how that change that we are going to be looking at from all the other variables that we can measure. I have a video here to show about the sun and its revolving position, but in the interest of time, I'm going to skip that particular video here, but we'll keep going. But I will come back to another video where we will talk about the greenhouse gas. So I'm throwing all the terms now, first of all, for bringing everybody up to speed. The one thing that I wanted to say here is that there is a greenhouse effect that is causing climate change. What is the greenhouse? What are the greenhouses, the gases that we see in the atmosphere? Carbon dioxide, methane, nitrous oxide primarily, and then fluorinated gases, water vapor. These are all considered to be greenhouse gas, and they are trapped. They are in the upper level of the atmosphere that is stopping the radiation that is coming from the sun to escape back to the atmosphere. So this is the radiation part that I wanted to kind of show in detail. And then what happens to the greenhouse gas because of the entrapment of the heat. So the blown up figure that you see, I'm not sure if the last row can see this graphic clearly. Is that clear enough for you guys in the last row? Good enough? No? Sorry? Lighting. Okay. Oh, okay, sorry. Yeah, these are small, but if you don't mind, if you want to come to the front row, please feel free yourself. But if the lighting needs to be adjusted, please take care of that. I'm not sure if that will help in any ways. But the arrow mark that what we are seeing is the radiance. The atmosphere, that is actually allowing the solar radiance coming into the surface of the earth. That is a big portion that we see here. And I hope it improves a bit. I'm not sure. Basically, that partitioning is happening. Some of them are intercepted when the radiation coming from the sun is reflected by the clouds. Some are absorbed by the surface of earth. And then again, the amount of heat that is emitted by the Earth's surface is going back into the atmosphere. But because of this greenhouse gas that we emit, or basically blocking the escape of this radiation, so that is coming back. So this greenhouse gas that is blocking the radiation is heating up the earth. The temperature increase that what we are seeing is because of the greenhouse gas. And of course, latent heat flux is another source of greenhouse gas. Latent heat flux or water vapor coming from the plants, coming from the wet soil. When the sun is heating up, it becomes water vapor and then it enters into the atmosphere. They are also a source of greenhouse gas. So ultimately, if you see, it changes from place to place depending on where you are on the earth, latitude and longitude wise. But the incoming radiation is actually partitioned into several components, and the outgoing radiation is also partitioned. So this is the radiation budget that these climate models are using to understand what kind of radiation change that we are looking at based on the land cover, based on the atmospheric conditions, and based on the location, because northern latitude versus southern latitudes, they have different incoming radiation. So all of those things are important, and it changes from place to place. I'm using the publicly available material to share this graphics here. I'm attributing all of the sources in my slides. So you can see the greenhouse gas is again enhanced in this graphic. Radiation coming to the Earth's surface is getting again back to the atmosphere, but because of the presence of this greenhouse gas in the atmosphere, they are reflected or they don't escape, they come back to the surface. And that is causing the warm up of this atmosphere anywhere from the land surface all the way up to 50 kilometer. That's the Earth's environment that what we are talking about. The change we are seeing is because of the trapped greenhouse gas in this layer in the atmosphere. Okay, so this is the basic greenhouse gas effect that we wanted to say. And more pronounced effect in this graphic that I'm showing here, they are partitioning these numbers. For example, they are looking at how, this is a simplified schematic, the radiation 235 watts per meter squared that is coming in. But how much is getting scattered, getting absorbed, and then when they enter into the land, of course, it heats up the land on a daily basis, right? When the sun rises in the morning at 6 o'clock, it starts heating up the air, it starts heating up the soil, then the whole atmosphere getting warmed up. Typical March, April, May months, if you remember in India, it really slowly starts in the morning and heats up, and then it comes back again to cooling nights in the evening. And the Earth radiation budget, of course, is modified because of this greenhouse. Not all of them escape, some of them come back. This is a positive feedback that what we are talking about here. When I'm saying positive feedback, there is temperature that's coming in, and that is trying to escape, but that's not leaving the surface. It's coming back again. Again, it heats up. That heat again heats up the soil. Instead of going back again, it comes again back. So that cycle, feeds itself back again.
So it reinforces the loop, the circulation. So that's the positive feedback that I'm talking about. I'm sure many of you are familiar with when I'm talking about these positive feedbacks, but this greenhouse gas is the main source of the circulation that's happening and the heating up of the earth, atmosphere and also the earth's surface. Okay? So, again, fundamentals, I just wanted to get to you first before I talk about other topics. When we talk about earth system and climate change, there are variety of sources of information to understand, right? Number one is the data. Data that you go out in the field and measure. For example, temperature, precipitation, humidity, wind speed, radiation, all of those variables you can measure with instruments mounted on the platform or mounted somewhere else. But there are also other tools like models. Climate models, for example, are used to simulate these atmospheric conditions. And in the climate change literature, they talk about climate models, generation 1, generation 2, generation 3, like that, right? Early 90s, they came up with CMIP, CMIP, coupled model interpolated model, something like that. In a coupled model intercomparison project, I'm sorry, coupled model intercomparison project, CMIP, version 1, version 2, version 3. Now we are at version 6, CMIP 6. That is using shared socio-economic pathways, or SSPs they call. We will get to the details of what these socioeconomic pathways are, but current generation models are using this SSPs to understand what kind of change are we looking at with respect to temperature. Uh, According to the data, of course, the last year was the warmest record on record in terms of temperature change from the long-term average. But of course, in the last 10 years, they are saying that this year was the warmest. And then next year came, they said this year is the warmest than the previous year. So likewise, in the last 10 years in a row, we are seeing continuous increase with respect to temperature based on observations. We are talking about the historic data based on observations. Now, we are training all these climate models to predict that, to predict whether or not we are seeing the same change in increase temperature, right? There are 5 scenarios. I'll come back to that. But again, please bear with me. This slide is a little bit crowded and mostly applicable to high latitude regions. But the idea is simple here. I'm going to repeat the same topic many, many times today. There are indicators, right? Like, for example, when you go to the doctor, when we are sick, they measure a couple of things. They measure your pulse, they measure your blood pressure, temperature, all kinds of things, right? So likewise, for planet Earth, there are indicators, there are vital checks that people do. These are the variables or health check indicators that I would say. For example, I talked about temperature increase already. That's one indicator. We talk about precipitation change. We are also talking about heat waves that is causing a problem. And then snow, drought conditions, sea ice level, Arctic sea ice extent, and then sea level, and then marine distribution, species distribution, heat of the ocean is another indicator, and then the growing season length, and wildfires, and then heating and cooling degree days. These are the variables that we measure, we observe, we collect data on, and say how they have changed. On the x-axis here, we are looking at 100-year record. If you look at the change, it is very significant in some variables. Like, for example, I'll tell you, sea ice extent in the last 50 years or so at steady decline with respect to how sea level ice content is changing. Sea level rise is also constantly increasing. And then wildfires, everywhere it is increasing now, especially in the US. And of course, heat of the ocean, which is an important element for controlling climate, is also increasing. General indicators of the health of the planet, that what we are talking about. I am now extracting all this information from a report. It's actually from Global Climate Report, but I will also show you an interesting video about one example of what I'm talking about with respect to ocean heat content and sea ice, and then Arctic ice melt, Antarctic ice melt, and all that. So it will be a very nice video to watch. But what I'm talking about is being repeated in that video, which will reinforce your understanding. The purpose of this graphic is to show you, it may not be detailed. Of course, you will have all this material available to you for your reference later on. And the reference is also available from the material that I downloaded, so you can get these also. The purpose here is to show, this is a global map on the background, what you see. I'm not sure if it's clear. You can see this is the temperature increase part, whether it is North America or South America, Europe, Africa, Asia, Australia, everywhere temperature is increasing. The change in temperature, what we are seeing on a global scale, right? It is changing. And then we are talking about hurricanes in the North American region, or extreme rainfall events, whether it is Africa or even in the Middle East countries. Floods are becoming more and more. Typhoon, as of today, probably Ditwa is one cyclone that we are seeing affecting coastal South, India, like Tamil Nadu to Andhra Pradesh and Telangana region, right? So there are changes. This is, of course, when we are talking about hurricanes, we are talking only about June through June, 1 year window. But what we are looking at here, the problems are global. It's not just in our place, it's not just in another place. It's happening everywhere around the world. Heat waves, droughts, floods, right? Landslides, and finally, of course, sea level rise induced problems all around the world on the coastal cities are very profound. We are witnessing a historic moment here with respect to all of these things. When I prepared the first set of slides using the data, it was 2023 data that I used. And at that time, I saw the report saying 23 was the warmest. And then within the last few months, another report came, it said 24 was the warmest. So you can clearly see the climate change literature is changing so dynamically. I'm not able to even fix my literature and say this was the warmest year on record, because it's changing on a daily or yearly basis here. 2023, based on that record, was the warmest, with temperature around 1.45 degrees C, plus or minus 0.12 with standard deviation that we have here, relative to the past condition, baseline period. Most of the time they say pre-industrial time frame of 1850 to 1900, when there were no industries, no manufacturing, no pollution, all of those things are taken out of the picture. So we are looking at 1.5 degree or below temperature increase. And if you remember, Paris Accord in 2015, when they all met, all the countries met and came to an agreement that we will cap the change in the increase in temperature to be 1.5 degrees C and below. For that, whatever is needed to be done, for example, mitigating or reducing the pollution, converting to renewable energy, minimizing the fossil fuel emissions, and all kinds of things they were talking about. But still, when the change happened, when the change is still happening, we are crossing this threshold already. Every year we are kind of increasing. Again, this accord is being revised or being discussed right now. What you are seeing here in the last 48 years, continuous record, 1976 to 2024, this planet Earth is steadily increasing temperature-wise. So the deviation from the 0 degree change is like above zero always, that I am showing here for the last 48 years. The planet is showing the signs of warming up steadily for the last 48 years. That's pretty significant. It is not hiding the fact, it's really showing the distress with respect to temperature increase. And as you can see here, from 1850, the change that what we are seeing here is below zero, right? But the change when we are talking about from 1950s, particularly from 70s, the steady increase with respect to temperature anomaly, change in temperature to the positive side, is pretty consistent. It's pretty consistent. This is what the climate change that people are talking about, what's happening in the last 50 years. And it is the data that we have collected. It's not the model. There are people who always say, what is the uncertainty with this data? How can we measure a model, or how can we understand these models? But no, this is based on the data that we have collected from the field, and we cannot say these instruments are wrong. Data, particularly coming from the observational records, are considered to be holy, sacrosanct. It cannot be really considered to be wrong. So with this data, people are saying that there is consistency with respect to temperature change. Again, I'm repeating this in the slide here with a blown up photo, just to show you that, of course, the temperature year after year after year, the change that what we see is coming together to confirm our findings. This is on a global scale, but this happens in every neighborhood that what we can relate to, with respect to temperature at least. Again, the blown up picture that I showed before, not so red areas when you look at last 100 plus years, but last 30 years alone, if you see, particularly on the higher side, lots of red areas, lots of red areas. The change is anywhere close to, 0.51 to 1.5 degrees Celsius, that what we see here. And this is very unsustainable for us to live. Everybody has some tolerance, but when the temperature is increasing, it is going to really cause discomfort, not just for humans, it's going to cause problems for animals, problems for vegetation, problems for all the natural ecosystems. Now, another interesting dimension that I wanted to show you, extracted from this annual report of NOAA, what we are seeing here is a long-term record, the anomalous condition with respect to three conditions here: El Nino, La Nina, and then ENSO. On a global scale, when you look at, this is temperature change, for example, what I'm talking about. When there is El Nino, the warming conditions are pretty clear, meaning you can see the warmer anomalies happening. When there is El Nino, the blue ones, you can see the cooling conditions. And of course, even in this case, under warmer conditions, post 1970s, even in El Nino years, we are seeing warmer conditions, but it is little bit lesser than your El Nino years. El Nino neutral, the gray areas, are not, kind of showing a steady increase. But these cycles happen every 5 to 7 years' time. This El Nino, La Nina, we will come back again to discuss this a little bit later. If not in the first lecture, maybe today or tomorrow I can talk about that. This is not in our control. This is climate variability indices, ENSO, El Nino, La Nina, and all of them. But every 5 years it comes, with respect to anomalous sea surface temperature, that they really predict what is happening with respect to temperature change or precipitation change based on these El Nino, La Nina conditions. This is also confirming that during El Nino years, you have more temperature, and some areas will have more rainfall, some areas will have less rainfall based on the location that we are in. This slide is again crowded, but one thing I wanted to convey, of course, is that the percent change with respect to precipitation, land-only precipitation, based on the observed data for 1 year, for example, that we are looking at. The darker green means we are talking about 200% change with respect to precipitation in this case. So there are a lot of brown spots, meaning they are really less than 100%, meaning even if they had received average rainfall last year, this year they did not get that amount of rainfall. That's what these brown spots mean. Many of the US regions and North America, particularly Europe, you are seeing in China. But if you see here, whether it is Afghanistan area or Central America or parts of China, you are seeing some heavy amounts of rainfall in the last 1 year. So it's a mixed record when you just talk about only one variable. We need to really understand a lot of other variables that are connected. Precipitation temperature are the primary variables for hydrologists because we use them. We will use them today in our class for downscaling temperature or precipitation, see how the changes are happening predicted by these climate models. And that will be a good exercise for you. But what I'm trying to say here is that there is always more and more of extreme rainfall events that we are seeing here. Why are we seeing all this? Again, coming back to climate change science here, we have more CO2 emissions in the atmosphere in the last 100 years, particularly in the last 50 years or so, if you see this steady increase. The source of CO2 are from many sources like coal, oil, gas. We are using all of them, right? These are natural resources, fossil fuel emission coming from the earth, of course, that we are seeing a substantial increase in how much gigatons of carbon dioxide that we are putting in the atmosphere is shown in this case. CO2 in the atmosphere has surpassed 417 ppm, which is based on the data that we have observed from Hawaii. Right? On a global scale, parts per million carbon dioxide in the atmosphere is going up. They will stay there for some time. Methane is also there. They will stay there for some time. Even if we control these emissions today, like I said before, the impact of those fossil fuel emissions that are already in the atmosphere will stay for some time, will stay for a couple of decades. And that will impact on hydrology, on agriculture, on fisheries, and many other things that we are going to be relying on and depending on for survival. Ocean heating and sea level rise. It's an important topic also, but I will touch, I'm just introducing you this concept first. Ocean is a heat regulator, right? Because it is such a huge, planet Earth is covered by vast amount of water bodies, right? 97%, right? So fresh water is only less than 3%. So that ocean is a big regulator of heat. It takes all the solar radiation on a daily basis, saves it because it has got a lot of thermal inertia. Unlike atmosphere, they can really store a lot of heat over time. Churning that sea is not easy. The heating conditions, when they change, they really show the signs of distress. For the last 100 years or so, heating is going on in the upper 2,000 meters in the sea. And if you look at this graph again, ocean heat content on a global scale is steadily increasing. You know, it is such a big water mass that it shows heating continuously, showing the stress of heating. And then, for example, in this case of 2024 heat content on a global scale, these are contours of global heat content, ocean heat content between 0 to 700 meters. Surface of sea level is 0, and then below 700 meters from the surface, they have measured the heat all around the world. This is India. This is Gulf states. US is here. Okay. The this is Pacific, and this is Atlantic, and of course, Indian Ocean is here, Indian Ocean. So they put the contours, as you can see here, there is a temperature or heat content is changing, is increasing. So because of that heat content, we are seeing the changes in the typhoons and cyclones and hurricanes that we see that's coming from the sea. You probably see from the weather reports that low depression is forming in Bay of Bengal or Arabian Sea, or the monsoon that's bringing rainfall to the coastal regions of Kerala here, or Bay of Bengal heating that is bringing cyclones here. If the heat content in the ocean is changing or increasing, that starts creating this water vapor. Under these warmer conditions, the atmosphere is drier and it can hold 6 times more moisture in the atmosphere. That's what the relationship talks about. When the atmosphere is dry and desiccated, it can take up all the ocean water vapor that's coming from this ocean surface and holds up. And then it starts dumping back right onto the ground, that heavy amount of rainfall. That's one theory that people are now justifying, that why are we seeing all these extreme events? It's because the atmosphere is so dry, so thirsty, and the oceans are putting out more and more water vapor into the atmosphere. They are holding up, and then when the condensation process starts, it starts pouring down right away. And that's the reason why we are seeing 24-hour rainfall of 100 millimeters, which is high amount, for urban areas like Mumbai, Delhi, Cochin, or other places to see that amount of rainfall to hold. So one system is connected to the other systems. This is all integrated. We cannot say, I'm going to not worry about the ocean, I'm going to worry only about flooding issue in my neighborhood. No, I think to get a bigger picture, you need to understand where the source of moisture is from, what causes this increased conditions, how are we going to track whether this moisture is coming from the land convective heating, or is that from the moisture transport through monsoon times, or pre-monsoon season, or post-monsoon season, or northeast monsoon, or southwest monsoon, or whatever. We need to really see the source of moisture. For hydrologists, precipitation is the source of input for any calculations. For atmospheric scientists, precipitation is the last term, is the amount of moisture the atmosphere is losing. They will consider that as a negative quantity, but for us, precipitation is the positive. That is the first source that we take it and then divide that into multiple components. So there is a difference in terms of how disciplines differentiate even one term like precipitation, but it can change, with all the other things. So I talked a little bit about ocean heat content. When I'm going to show you this video, you will understand a little bit more about how the connections are happening with respect to ocean heating, to sea ice melting, Arctic glacier melting, all of those combined. There are 10 or 11 indicators that I talked about. This particular video talks about it so nicely. So I'm going to play this and see whether or not the audio coming.
Sheets of ice. In some places, that ice is several miles deep. This massive continent, as big as the U.S. and Mexico.
We continue now with our series from Antarctica. The ice-covered continent is being transformed in part by climate change. Antarctica's ice, which contains the vast majority of fresh water on Earth, is melting at an accelerating rate. William Brangham and producers Mike Fritz and Emily Carpeau travel there and have this report on how coastal communities all over the world could be impacted. It's part of our occasional series of reports, Peril and Promise, the challenge of climate change.
For as far as the eye can see, Antarctica is covered by thick sheets of ice. In some places, that ice is several miles deep. This massive continent, as big as the U.S. and Mexico combined, has for millions of years been home to some of the most breathtaking examples of ice on the planet.
What you can see behind me here is a very good cross-section of a glacier in Antarctica. And what you can see with all of those different layers, that is hundreds and thousands of years of snowfall and precipitation stacking up one on top of the other and slowly exerting pressure downward on those layers of snow. And that's basically how a glacier is formed.
But Antarctica's ice is now increasingly being threatened, and most researchers believe it's because of climate change. According to one recent study, the continent's ice is slipping away 6 times faster than it was 40 years ago.
And Antarctica is now losing 252 gigatons of ice per year.
Glaciologist Joe McGregor is part of the team at NASA's Goddard Space Flight Center that's studying Antarctica's ice. Using radar and lasers, they measure the thickness of the ice, how it's moving, and whether it's growing or shrinking. This animation they build shows a sped-up version of how the ice flows on the continent.
Help me understand what that means, 250 gigatons.
A gigaton is a billion metric tons of ice. And when you do the math, you wind up with the Antarctic ice sheet is out of balance by more than 3.5 swimming pools per second.
Every second, 3 Olympic-sized swimming pools worth of ice is disappearing from Antarctica.
Yes, and considered on average over the year.
Just to put that in perspective, in the amount of time it takes to watch this story, Antarctica will shed more water than New York City uses every day. The warming that's causing this ice loss varies in different parts of Antarctica. Here on the peninsula, the long branch of land coming off the northwest corner of the continent, warming has been especially pronounced. At the Vernadsky Research Station, which is run by the Ukrainian government, meteorologists like Oleksandr Poluden have been keeping some of the longest-term temperature records on the continent. While it's warmed and cooled at different times, Poluden says the overall trend here on the peninsula is clear.
You will notice that the temperature doesn't tend to increase all the time, as there are certain fluctuations from year to year. However, it becomes evident that over about 70 years, the average year-round temperature has increased by 3.5 degrees.
It's becoming clearer that parts of Antarctica appear to be unstable and are losing ice much faster than we expected.
Michael Oppenheimer is a climate scientist and professor of geoscience at Princeton University.
As bouncers in the bar, leaning up against the door and keeping the ice from flowing into the ocean.
But as the atmosphere keeps warming, major ice shelves in Antarctica have also been collapsing. In 2002, the Larsen B ice shelf, the size of Rhode Island, completely disintegrated. These are satellite images of it breaking up into hundreds of pieces. As predicted, the glaciers that Larsen B anchored up on land began accelerating towards the ocean. And then, 2 years ago, the even bigger Larsen C shelf, this is it from the air, developed that miles-long crack in it. This shelf, which sits in front of the Thwaites Glacier, is also crumbling. And part of the Brunt ice shelf is expected to break off any day now, releasing an iceberg that'll be twice the size of Manhattan. There's still some debate over whether human-induced warming is the only thing causing these changes. Antarctica has lost ice many times before, and that also caused the seas to rise. Researchers are now trying to determine how much warmth it takes to cause truly catastrophic sea level rise. That massive glacier that you see behind me connects all the way up above those peaks to the enormous West Antarctic ice sheet. And all of that ice and snow contains a remarkable history of Earth's past climate.
It's like a tape recorder, 10,000-foot tape recorder in places. And so scientists have drilled ice cores through the layers as far down as they can get, and then they analyze those layers.
Glaciologist Robert Mulvaney, that's him in the black cap, works for the British Antarctic Survey. He and a small team have been drilling over 2,000 feet down into the ice sheet and pulling out these ice cores.
What we've been trying to do is recover a climate record of the last glacial cycle, so the last 120 to 140,000 years, to try to understand how our climate might change over the next 100 years or so as the climate responds to increased carbon dioxide in the atmosphere.
The evidence from these cores and many others indicate that when the Earth's climate was just a little bit warmer than it is today, the world's oceans were over 20 feet higher.
So 120,000 years ago, when the climate was probably 2 degrees warmer than today, the sea level was maybe 6 to 9 meters higher than today.
Given the uncertainties over how serious sea level rise will be and over what time span it'll occur, Michael Oppenheimer argues that there's still time to act and to prepare.
doesn't mean we should all throw up our hands and run. Let's start thinking straight. Let's start thinking fast about how we're going to help people, how we're going to help settlements, how we're going to help countries deal with the outcome. Because a lot of it is not going to be pretty. It's going to be expensive and it's going to be disruptive if we don't get our act together now.
Yeah, instead of me talking, I thought showing that video will help us understand the spatial, extent of the change that we are seeing in Antarctica, for example. Those glaciers I have seen up close, and it'll be surprising to see the height of them. It's very difficult to get that 3D view by watching here. I will tell, it's about 20, 30-story building that what I saw in front of me, even collapsing in Alaska. Last summer I was there and I could see. And it's massive. The change what we are already seeing there is humongous. And that report is kind of nicely highlighting that. So the sea ice, is melting. Arctic glaciers are melting. Antarctic glaciers are melting. So they are adding water in the sea. And then once they melt, they can absorb more heat. As you know, white snow surface, white cover reflects more instead of absorbing the heat from the sun. But now they are all melting, so the black body radiation of water that actually can take up more heat is also adding. So the ocean heat content, I wanted to bring that whole circle into this discussion, saying how the ocean heat content is increasing is because of this, the loop, positive loop or adverse impact that what we are seeing is the reason why we are seeing. So I'm actually going to check with your need on a break. Do you want to have a 5-minute break now before I proceed? Or want to stretch yourself or keep going? Any suggestions? Anybody needs a break? Please raise your hand. Don't feel shy. If not, I can keep going. Let's proceed then. Seems like majority. Okay, that's good. So we are a little bit behind actually because of all the issues here, but hopefully we can catch up, no problem. Like I said before, the extreme events are all around the world actually. Heat waves, flood disasters, tropical cyclones, droughts are happening. And of course, we are, as humans, of course, are causing. Of course, we need to understand how it's impacting. For India, for example, the realization is already there, which is very impressive. I mean, we have understood there are impacts of climate, leave alone the climate change part. The change in climate itself is happening in front of our eyes that you all see that, witnessing, right? And how is it affecting? How can we contribute to science that will improve data-based decision making is the part that we are all interested in. Now, let's not go into the depth of what kind of advancements we can make in terms of predicting climate change. No, we will leave that part for climate change analysts or climate change scientists. But we want to understand from civil engineering side, from water management side, from disaster side, how can we understand the change that we are seeing on the planet Earth because of this climate change? How can we use the data to really develop some understanding? That is the question that we want to be understanding from here. And one other thing with respect to climate change that I wanted to highlight here, they say this is a new normal. The term that you will come across is called new normal, meaning you probably saw that 0 degree or 0 line, right, for temperature or precipitation, and then we call anomaly. Anything that changes from that 0 line is called anomaly. Positive anomaly means it's above the 0 line. Negative anomaly means it's below the 0 line, right? And now this changing condition, they say it's a new normal. It's not, 0 is not the new, original normal. Now the new normal is something totally different. To avoid any adverse impacts, they say couple of things people can do. Not just by one individual, but by group of countries all around the world have to do. 3 things in climate change literature that you will see. One is mitigation, right? The other one is adaptation, right? And then the third one is, of course, impact assessment. That comes in the middle. There are differences between these terms. I'm sure you understand a little bit about them. Can I ask the audience, about what do we mean by mitigation. Can somebody answer the question? What do we mean by mitigation? To reduce the costs, good. Basically, we are talking about the cost basically is greenhouse gas, the emissions. We want to reduce that, right? What is adaptation? Okay. Okay. To reduce the impact or to face the shock and to be resilient to withstand those impacts, right? In other words, of what you are saying. And what's your name? Priyanka? Priyan. Priyan. Okay, I'm sorry. Yeah, Priyan. So what you are talking about, Priyan, is about mitigation and adaptation, right? But before you do the adaptation, we have to understand the impact of what kind of change that we are seeing. That's what we are here for, to understand what kind of impact. Flood is an impact, drought is an impact, heat wave is an impact, landslides is an impact. But then how do we adapt? We want to really build stronger infrastructure. We want to really come up with early warning system for floods. We want to really store more water to avoid drought, conditions in the reservoirs. So those kind of adaptations. So the impact is in the middle between mitigation and adaptation. Mitigation, we are not in that field. In this group, I don't think we are needing to be worried about mitigation too much, because um, of course, it comes up with renewable energy, for example, minimizing fossil fuel emissions, minimizing or making more hybrid cars, electric vehicles. Those are the things that are happening. But I think in this crowd, when we are talking about hydrologic extremes, holistic view, we want to have an understanding of what kind of emission changes that we are thinking about, but our focus should be mostly on the impacts and the resilience or the adaptation side of things. So be clear about these terminologies. People use it interchangeably or mixingly, but I want you to be appreciative of the fact that these terms have certainly different meanings, and you cannot just throw these words randomly. Okay, and then of course, data science, management, global scale mitigation, all of those things are really needed, and it's again needing international collaboration. And maybe it's already happening in many levels, and it needs to happen more for really looking the change on the ground by many of the vulnerable countries. When I'm talking about vulnerable countries, they are the countries that do not even produce emissions, more emissions. Majority of those countries don't even produce that much. I have some graphics to show on that, but I'll see what I can show. So I'll come back to that again. But I just wanted to interject and say that these are the terminologies people use. So by the end of this class, you should be all familiar with these terminologies: mitigation, adaptation, impact assessment, right? And then now repeating this SSPs, shared socio-economic pathways, or the scenario that people want to come up with or understand for climate science. Okay, there are 5 SSPs that we have. This is the 6th generation climate model assessment. It started in 1990 or 1988 around, but every 5 years they kept coming up with a new generation of climate model simulations. And then they called with different names: CMIP 3, CMIP 4, CMIP 5, now CMIP 6, right? CMIP 6 is the one. CMIP 6 is the one. If you're all going back and starting your research, I would suggest, of course, to look at SSP scenarios for your climate change assessments. What are these SSPs? There are 5 of them, like I said: SSP 1, 2, 3, 4, and 5. Each of them have come with a radiation forcing limit, and then they call it, one is very conservative, the other one is called extreme, highly non-conservative, and then different, conditions in the middle that they talk about. I'll come back to that little later here. Yeah. So what we are seeing here, these 5 scenarios are used either in RCPs or SSPs when we talk about RCPs are the previous generation climate model, SSPs are current generation climate models. One considers socio-economic pathways more importantly, like population, density, and how much of community impact that we have. All of those things are explicitly included in this version of climate model scenarios. In the previous generation, they did not include. And of course, you have 5 scenarios, like I said, SSP 1, 2.6, that is radiative forcing. That is watts per meter squared, what we are talking about. 2.6 watts per meter squared as the radiation forcing, radiative forcing. Most conservative, meaning if you stop emitting greenhouse gases as of today and curb all the emissions, you are going to see planet Earth cooling or greenhouse gas effect coming down. And it will be the most ideal situation, right? This is the most ideal situation. The worst situation, 8.5 watts per meter squared with SSP 5 scenario they call. That means nobody wants to control emission. Nobody wants to worry about how much pollution they make, but they are going to live as is, without any change in their practices, polluting as much as possible, emitting as much as possible, thinking nothing will happen. So the worst case scenario, climate change will create significant change with respect to temperature increase, precipitation change, and all that. So the remaining 4 scenarios that what we are talking about here, whether it is SSP 2, SSP 5, between 4.5, that is a middle of the road scenario they call, versus a little more aggressive one, SSP 3, that is 7. Regardless, I mean, there are uncertainties. Every country is different. Population is different. India, for example, with 1.4 billion and more, we are talking about policies that will reduce emissions, talking about how to really make sustainable living, lots of things. Every country is doing in one way or the other policies that are based on science, based on their economic conditions and so many other factors, which we don't need to worry about. But what I'm saying is there are some uncertainties associated with those. So that's why people in climate change literature, they are talking about these scenarios. What if that scenario happens? What if this scenario happens? Then they come up with, if that scenario happens, your precipitation or temperature increase will be this much. If this scenario happens, it is going to be this much. So for relating to a specific scenario, it's very difficult. But as hydrologists, civil engineers, water management people, what we want to see is to bracket those uncertainties. We want to cover those uncertainties and make some probabilistic estimate on what is the risk of having flooding based on the range of precipitation that we have, based on the range of other variables that are impacting flooding or drought or whatnot. So for that reason, we want to consider as many models as possible to accommodate uncertainties in our assessments. Again, I don't want to go into the details here. The change in temperature, precipitation, Arctic sea ice, or sea level change, you can see, depending on what scenario we pick, anywhere from 9 meter or 3 meters, or less than a meter height increase in sea level. So people are trying to really accommodate these shaded areas with all these brackets that we have, uncertainties associated with each one of those scenarios, SSP 5 versus SSP 1, you have changing predictors, temperature or precipitation. Consistently, temperature is increasing, precipitation increase is not certain. In some places you will have more, some places you will have less. And in some places you will have the same amount of precipitation. But what is the difference? The difference is, like for example, it could be Kozhikode, for example. You will get an annual amount of rainfall of, let's say, 2,000 millimeters. It may not be coming in the season that you want. It may be coming all at once, or 2 big spells of rainfall and no other rain after that. So you will get the same amount of rainfall but in big chunks, right? So that is not good for water managers. That's not good for agriculture. That's not good for hydropower production or flood protection, whatnot. All kinds of issues that are coming up with. So even if you get the same amount of rainfall, but if it comes in short spells of heavy duration rainfall amounts, when you add them up on a total annual scale, even if it does not show a change, it does not mean there is not a problem. There is a problem. That's what I'm trying to understand or explain here. Okay. So with that, I'm going to keep going here. I think we repeat all of this. I think I'm going to skip in the interest of time here. You know, we are talking about global scale precipitation change, and temperature, of course, is consistent. But as you can see here, they talk about SSPs, right? Now you have to really, you know, when you read literature, you will understand when they mean what they mean by SSP 1, 2.6 versus SSP 3.7 and SSP 7. Sorry, SSP 7, that is this one, and the SSP 2.6. But you can see on a global scale, there is such a big variability. I also want to emphasize one thing here. It's an opportunity, right, for us as hydrologists, as people who want to really do a good job with respect to water management. This variation is an opportunity for us. If it comes the right amount of precipitation at the right time, and you have model built, you have infrastructure built to accommodate all of those changes, you and I will not have a job. Now think like this, that is not happening. The change is constant. This year is not the same as last year, and next year will not be the same as this year. So what does it bring? It brings an opportunity for us. They will come to you, say, design this system for me, because I don't think the existing system is working. So like that. So I'm just giving you an example. We are in the right profession to deal with this kind of a challenge in the right time. That's one thing that you want to take away from here in this class. That if you really understand your role in contributing to this chaos or confusion or uncertainty, whatever you call, this is an opportunity to contribute to basic science, to improve applied science, to make improvements to the society and things like that. So that is one thing you can remember. Again, Director also talked about it. I just want to introduce the term. Some of you are familiar, some of you may not be. SDGs are Sustainable Development Goals developed by United Nations in 2015 or so, and then they are trying to achieve this. No poverty, zero hunger, good quality education, examples I'm giving, right? Life below water should be sustainable. Life on land, it relates to us, right? And then we are talking about clean water and sanitation, which is our domain, right? And then we want to talk about climate action. So there are many SDGs are directly related to what we do. When you are writing a project or a proposal, your target should be one of these development goals. Again, basically to think about, can I contribute to no hunger or zero hunger issue? What do we do for that? Relate to climate change and then see where can we really play a role. I will now relate this to SDGs to one example here. Let's say atmospheric carbon dioxide, right? That is the indicator that I talked about in the beginning. CO2 constantly is increasing in the last 30, 40 years. We have reached to a point of 417 parts per million. What does it mean, right? I mean, we talked about hazy, fundamental, abstract stuff, but I want to relate to now the SDGs. When CO2 is increasing in the atmosphere, what happens? Enhanced greenhouse gas that we saw just recently in the past few slides. Ocean gets acidified, variation in crop productivity. More carbon dioxide in the atmosphere means more CO2 fertilization for the plants. They grow well, they are very happy. They put out more leaves, they produce more grains sometimes. And of course, nutrient content is changing, air pollution is more. So all of these things lead to food insecurity in this case. And then what are the SDGs that are directly related? Climate action is impacted, life below water is impacted, zero hunger is impacted, and of course, health is also affected. Health and well-being is also affected. So now one indicator of increasing carbon dioxide emission relates to some of the issues and then how these SDGs can be related to that. So it's a full circle. So likewise, for all the 10 indicators that I talked about, they talk about the impacts and they talk about how that will affect SDGs. I would say in that report or even in my slides, I'm going to actually show you like this. For example, temperature increase. It's a very easy variable to relate to. What happens when the temperature increases? Floods, droughts, heat waves, and wildfires. We know that, right? It's happening, right? When the flood is happening or drought is happening, water problem happens, displacement, built infrastructure, degradation that we all know. So likewise, you have all these impacts. If you even pick one, global temperature increase, what's happening to Calicut with respect to declining agriculture? That's a nice, directly related science question. And how does it really impact the sustainable development goals? There are, how many of them are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 variables. 13 SDG goals are impacted just because of one variable increase on a global scale. So you are able to relate, like what are the impacts because of one variable increase on a global scale and how SDGs are impacted. So I'm just highlighting one thing. Likewise, you have ocean heat content. For example, if you see how ocean heat content will change, so many other factors, and what are the SDGs are related to that. So maybe it provokes your thinking in terms of understanding sea level rise, another interesting variable that we are all going to be directly impacted one way or the other. You saw the Arctic, Antarctic ice melting, right? We talked about sea level rise and then causing coastal flooding and erosion. Cochin is one place that we all should be worried about on the west coast. Mumbai is another place. Chennai, Kolkata, those are the places people are looking at. And then, of course, bigger cities like whether it is Tokyo, New York, Miami, on the West Coast, San Francisco, all of those places in the US. When things happen with respect to sea level rise, we are talking about infrastructure degradation. Seawater intrusion is happening in many places. Probably you are seeing that in Kerala also in some places. It's happening on the east coast of India. Biodiversity loss is happening. Reduced livelihoods, displacement is happening, more conflicts are happening, food security is also because of sea level rise. So these are the SDG goals that are going to be directly impacted because of sea level rise. So that is the kind of thing I want you to take away from what's happening with respect to the pulse check of this planet Earth, how it is going to affect the individual impact at the local scale to regional to national scale, right? Now we are not even talking about the national scale. So now if you're relating this local scale issue, sea level rise, which is happening probably in one city or one district or one coastal town, can actually be spreading to many places, right? So that's how I want you to think about both on spatial scale and also at the impact level, how many millions of people are going to be impacted. So there is plenty of things to contribute in terms of science when you take some of these topics. So likewise, I'll actually skip in the interest of time for all these variables here. Again, these are taken from the reports, right? So I'm going to make these reports available. Those who are interested, instead of using the class time later on, you can read, refresh yourself, and these are going to be out of date soon. Another year or so, if you're trying to really relate to this report, it's probably out of date because things are changing so fast. I wanted to tell you one more thing here. This is a global scale map, right? I mean, this is how they really relate to. I don't know whether I can close this here. Can I close this one? I think so, because it's hiding the view. So what they say here is climate change has impacted human and natural systems across the world who have least contributed to climate change being most vulnerable. It's a very powerful statement, meaning I think I alluded to this point before. The countries that are polluting less are getting impacted. That's what they're saying. Each of these hexagons or regions, so let's say SAS means South Asia, right? South Asia, that includes India, Bangladesh, Sri Lanka, Nepal, whatnot, all those countries. So observed changes, there is significant increase, in this case, extreme events. It's also, South Asia is also increasing heavy precipitation. Agricultural drought is kind of in the middle of the ground for South Asia, India included in this. I'm talking about on a global scale, right? So this is a global scale map. So if you look at South Asia, that is a big region still. In India, and then within India, if you look at by states, things can be different. But this is a conglomeration of all kinds of regions and areas. They come up with a general prediction of saying there will be more hot extremes for us, more heavy precipitation, and agricultural and ecological droughts are going to be also iffy for many regions within South Asia. So that's one interpretation. And then they are also telling in this report, like I said before, these are the emission amounts for most of the countries that are less zero emissions are the most vulnerable. This is a vulnerable index here on the y-axis. See here how many countries that are clogging here in this area. They are highly vulnerable even though they are producing very less CO2. There are some countries that are producing high amount of emissions, least vulnerable, right? So the disparity is very clear in this kind of analysis. The disparity of impacts by people that are going to be affected are quite clear. Human systems and natural ecosystems, if you look at Asia, we are going to have adverse impacts in some cases. For example, water availability, we will have adverse and positive impact. This is a very complicated diagram, lots of information. You want to read it peacefully. I'm quickly interpreting this for you. When they say the slashed green line area, adverse and positive impacts, what does it mean? One example, India will have more rainfall. Is it a good thing or a bad thing? Having more rainfall is a good thing or a bad thing? Tell me. Okay. Okay. That's one way of looking at it. Okay. 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 Sure. One argument is that excessive rainfall is a problem. I buy that. I don't deny. Is there a possibility, another counterintuitive thinking, what about storing that water, saving that water when we don't have? How many months in a year are we getting the rainfall in India? Can somebody tell me? What is the maximum number of months that you get rainfall in India? In any region, you don't choose a bigger region, but I'm telling your region, for example. 3 or 4 months. The remaining 8 months we are dry, right? What if we save that water, conserve that water, more storage, will help us to augment groundwater storage, minimize the loss. Instead of letting it go into the ocean, you could probably harvest every drop of it. So a good water management might actually reverse the situation from worst bad condition to probably a moderate good condition even. That's what they are talking about here, adverse but positive impact, depending on the solution that we come up with. We engineers can think about a solution for this unique problem. When there is excess water, it's a problem if it comes in the wrong time, wrong place. Urban areas, paved areas, you don't have storing opportunity there. You have to safely evacuate that water, drain that water away from the area. But if it comes in a pristine watersheds and areas that are not populated, build some structures, save that water, manage that water effectively, then it becomes a positive effect, right? That's not an easy solution. Can you build a dam? I'm going to actually even confuse you more by asking this question. In this green era, you cannot recommend that we need to build more dams. There will be a lot of resistance for that too. So then what is next? You need to come up with an alternative solutions. Have you heard of nature-based solutions? That's a new type of research area, but people are talking about. You don't need to build big structures to really store water. You can distribute that storage with multiple tanks, multiple ways of percolation, green infrastructure, to many other things to really store that water. So, innovation. creating opportunities and saving that, excess water that we don't need in 1 month can be used for the remaining 8 months. 4 months a year, remaining 8 months, we have to rely on that water, right? We are already talking about water scarcity in India for the summertime already. Even though there are some places that are getting flooded today, we are going to see scarcity problems. That is an interesting problem to have for us as engineers to solve that problem. So I'm trying to really, make your thinking go in a different direction. So I'll come back to the slides again here. These are carbon emission quantities by countries they talk about. South Asia, Southeast Asia, all of these regions are really low emitters of carbon dioxide. That's the message that you should get out of it. We in South Asia, we are somewhere in the middle of the global carbon budget. So we are not polluting more, we are not really adversely affecting climate, but we are impacted. We know climate change is happening here. So we are at the receiving end of climate change impacts. So that does not stop us thinking about a solution, but you need to understand where the problems are. So that's where I'm trying to come up with. Now, even thinking about sea level rise, 64 million people are going to be affected here. Cities like Mumbai, Kolkata, Chennai, Visakhapatnam, and Kochi, example cities that I'm talking about, are going to be impacted by sea level rise. Millions of people are going to be impacted, even though they are not to be blamed for emissions. And sea level rise is also causing problems all over the place with respect to increased sea level rise. Food security, ultimately, with more heat, our crop yield is going to go low. Water availability will go low, right? And the income drops. Livelihood is affected because of that. So there is a loop that what we are talking about. So whenever we are talking about, I started my inaugural speech talking about data-based decision making, or making decisions using the data, or providing data for policymakers to make decisions, right? All of those things are combined in this graphic here. We need to really understand the impact, and we need to understand how can we come up with a solution that will improve the livelihoods, improve the income, improve the farmer's life, whatever it is. So that is a kind of an example that we are talking about here. When, you cannot solve a problem by just looking with only one prism. You have to really see the holistic view of integrated assessment of an issue and then come up with a solution. Okay? Again, I think the scenarios that we are talking about, you are somehow familiar with some of these 1.5 scenario, 2 degree, 3 degree, 4 degree. SSPs are different. This is temperature increase that they are talking about. What if you have 1.5 degrees C? That is what we are seeing today, right? As we see today, this is the world we are in with respect to risk of species losses. Many species are getting lost. If it's going to go to 4 degrees C, there is going to be really adverse impacts. The same thing they are talking about, human risks, heat-associated health illness, disease with respect to higher conditions. India is really, really red on many things here. Food production, India is impacted when the temperature goes up. And then maize yield will be affected. Fisheries, we are all familiar, right? Coastal India gets a lot of fisheries, yields, and they are going to be impacted. So you don't see any field that is untouched, any sector that is untouched. Many sectors are touched, many sectors are impacted. That means there is plenty of opportunity for us to come up with solutions and provide that solution to decision makers. I have a second set of slides that I wanted to cover, but I can come back to this water unified concept. These are basic stuff that I will talk even tomorrow to begin with before we go next. I have India-specific climate change discussion. I can breeze through that if you permit me in the next 20 minutes, and then go from there to our next lecture tomorrow. Will that be okay? We can finish in 20 minutes? Because this is more important for you all, I think. So I talked about couple of things here, right? So I'll show you this. You are familiar with this basic stuff before I go to the India specific thing. A repeat of what you already know as water cycle. I'm not sure if it will play. Let's see if I can play this. More water vapor is going into the atmosphere, so that forms clouds, right? So low level clouds, high level clouds. What happens to the radiation with the clouds? They get reflected back. So that's a negative feedback. The surface is cooling. When the high clouds are there, more clouds produce more water vapor and more heat coming back, and that's a positive feedback. I'm trying to really quickly illustrate this. Do you follow what this video says? So the shallow clouds letting the heat to escape from the surface. So increased evaporation creates cooler conditions in the lower surface when the cloud is shallower. When the cloud is higher, the heat that escapes gets trapped and it does not go. It's greenhouse gas effect kind of a thing that creates warmer conditions again, creating a positive feedback. So positive feedback means again more water vapor will be lost, more high level clouds will form, and that can actually allow more heat to come, more heat trapped, more water vapor creation. So it's a positive feedback. So an example of how active the atmosphere and the land surface or the ocean surface behaves is illustrated in that nice example. So I just wanted to share that. I'm going to stop there, but let's stop sharing my screen or share my other screen. Okay. So the learning goals for us to understand a little bit more about India, right, in this case, and understand what the definitions of thresholds and extreme weather events. This is extreme events class, holistic view of extreme events, hydrologic extremes. So I'm going to relate to some of the terminologies here, and then looking at the regional impacts, what kind of monsoon impacts that we have, how do we really use the tools or develop tools, right? That is something that I wanted you to take away, at the end of this week, not today itself, but these are some of the papers I wanted to highlight because they talk about extremes. You may see them interesting and you may even update these studies. These are a little bit of dated studies, 2017, most of them are. We talked about precipitation climatology, rainfall extremes, and drought conditions in these papers. I'll take some of the examples from these papers here. If you look at India, it's really big, right? Like river basins or regions by geography or whatnot. But then look at the cities. And then what we did was looking at annual rainfall, monsoon rainfall, 1 day maximum, 10-day maximum. And then we looked at how each city is behaving. Basically, if you look at some cities, Kochi, for example, right, monsoon rainfall, there is a declining trend, what we saw based on historic records. This is from 1900 to 2015 or something, 115 years of IMD record. Basically, it's observed precipitation that we used. We looked at annual rainfall, monthly, monsoon, 1 day, 10-day maximum. And we found out the signals are mixed, that's the message. But again, precipitation, you cannot really draw conclusions over a large area. You'll have to understand what's happening in your neighborhood, in your backyard, in your watershed, whatnot. That kind of a localized information is needed for water management. So in this case, that's what we were doing. And what's happening here, I'm not sure. Let's see. Okay. Rainfall extremes, then we looked at by basins. Okay. These are smaller basins divided all over India. Red means, of course, we are talking about more extreme rainfall events. And especially if you divide this year, 1901 to 2015, but anyway from 1900 to 70 and from 70 to 2015, more red areas. So this falls in line with what these global predictions are talking about. Even though those global models that I mentioned before are recent ones, this is a little bit before that. By dividing 70 as the pre-industrial and post-industrial period, we found out that many regions within India are experiencing increased amount of rainfall, right? 95th percentile of rainfall or 90th, 99th percentile of rainfall is really going up in the last 50, 65 years. And drought, you know, you might be wondering, right? I mean, I asked this question before. We are talking about more rainfall. That means we should have plenty of water, right? But that's not the case. We are also looking at drought problems in India because we are getting this rainfall in 4 months' time. The remaining 8 months, unless we manage that water, there is no scope, there is no hope, there is no possibility for getting that water available for the remaining months. IMD versus multimodal ensembles here, what we are talking about. These are climate model previous generation RCP 4.5, right? From 2010 to 39, 40 to 69, 70 to 2099. You look at the duration, 4 months, red areas, you are going to have the most of central region, we will have drier conditions, drought conditions. These are bread baskets of India. Gangetic plains and Godavari, Krishna, all of those basins are going to be impacted. And of course, we look at the occurrence. How many drought events are we going to see? Many regions will have extreme drought events because of climate change. So I'm talking about historic precipitation data and the future drought data. So what is the connection here? We are talking about the necessity of water management in a country like India. Otherwise, these red areas will become more red. So it's in our hands to make these red areas greener. More sustainable operations, more water management decisions to be made, more tools to be developed, more technology should be coming up with. So anyway, again, total number of rainfall events, if you look at number of events and magnitude of those events, extremely high. Whether it's Kaveri Basin or West Coast, Malabar regions or Central India or Eastern India, you are seeing extreme events more and more. And 1, 2, 3, and 5 day maximum rainfall is also more or less happening all over the country. And extreme events are really not something to be kept aside. So that is something we need to really take it seriously. And these papers are going to be useful, but I'm also referring to this report. It may be available online that you can search. If not, I can send you them. PDFs will be available to you. All I'm trying to say is they started talking about nicely relating IMD based precipitation extreme events and then come up with annual scale analysis by every region. It's very important. There is plenty of things to do, plenty of things to learn from this report, but there can be plenty of other things that we can extrapolate from this report if you want to further. The main thing I wanted to say, but we will come back to this slide again later because, I mean, not this slide, but there will be repeat of some of these discussions. Extreme events, right? We are talking about more and more of those terms. They are listing about 8 terms here: extreme lightning, heavy to extreme rainfall, heat waves, cold waves, snowfall, cloudbursts, cyclones, and other events. But we are talking about 4 extreme events in this class for the next 4 or 5 days. We are talking about extreme rainfall amounts, heat waves, and also drought, which is not included here. That's an opening for us, right? And then landslides, which is an important topic that's also not included. So you can see the report is complete in some sense, but there are opportunities for us to do some research on these topics. Now coming to the definition, this is based on IMD research, heavy rainfall, anywhere from 64.5 to 115.5 millimeters in 24 hours. They call it, it's about 2 inches of rainfall, 2 to 3, 4 inches of rainfall, let's say, in 24 hours. Heavy rainfall. Many cities in India cannot handle that. And we are talking about very heavy rainfall from 115 to 204. Extreme heavy rainfall more than 204. This is based on IMD, set definition of 3 different categories of rainfall. Take your own data from your own neighborhood. you identify how many heavy rainfall events you saw in the last 115 years, how many very heavy rainfall, how many extremely heavy rainfall events. Of course, you need to have high resolution data. Sub-daily is good, but at least if you can do that on a daily time step, it might even give you a good idea about how many heavy rainfall events that each of your study area has gone through based on this index alone. That will give you an idea about what extreme events we are talking about. Heat waves, for example, departure of 4.5 degrees C to 6.4 degrees C from normal maximum temperature. India is going to go through really, a lot of extreme heavy heat wave events, right? So we are talking about May temperature. 40 degrees Celsius is already high. Maybe Kerala may not see that. I'm saying, let's say central India. 40 is already hot. If you add 4 degree to it, it's unlivable. And I experienced that when I was in NIT Warangal. One day it was 47. They told me not even to come out of the classroom, building or guest house. They say it's going to be burning hot. 47. And humans have a tolerance limit of 50 or something like that. Delhi saw that 50 degrees a year or two ago. I don't know how many remember. But, we are seeing these limits that are getting pushed on a year by year basis. Heat waves is going to be a biggest extreme event that India will have to be worried about, apart from heavy rainfall. And drought, we will talk about drought on day 3. How do you assess drought? What type of drought that we need to understand? How rainfall, missing rainfall amounts are relating to deficit rainfall, to drought conditions. We will talk about that. But then with heavy rainfall, if this amount of rainfall happens in Kerala, what kind of landslide issues that we are talking about? Saturation of ground cover, loss of vegetation on the hill slopes, development that's happening in Uttarakhand or other regions that may really, need to be considered for, designing certain things, for example. And how do you quantify these extreme events? What kind of triggers that we are seeing, and how can we monitor, how can we really come up with a early warning system? For all of that, you need to understand what is the existing thresholds, how do they define this? So this particular slide might be of real use for you to define these variables and how do they call extreme event as an extreme event, right? For a given event, whether it's landslides or floods or droughts, right? So that is something important. And I'm going to skip some of these, rest of these things extracted from the report in the interest of time, but you can read them later. The main idea is every year these extreme events are happening regardless of the region that you live in. It's not that any place is safe. Every place has got its own issues in one form or the other. If you consider those 8 extreme events that they have listed, one or the other region will have these one or the other extreme events. 2023 alone, 3,287 people lost their lives, right? In 22 states. It's a big area that we are talking about, and union territories. And that number is going up year after year. And the incidents are getting more and more. And because of the population, the density and the concentration, where it happens, all of these things are having a multiplying effect on the casualty, on the livestock of lives of the humans. And then you are also talking about million hectares, 2.2 million hectares of land or crops that were damaged because of heavy rainfall or drought, right? So these are the issues that we are talking about to address as an impact. So we talked about mitigation, adaptation, and the impact part is in the middle, we said, right? So the impacts, if you understand, then we will come up with a plan for adaptation. Then you can come up with a plan for making systems better, prepare for the future, right? Those kinds of things. So this report is based on the data that happened over the last year. They kind of renew this on a yearly basis, 23, 24, 25. So I am sure you will be now excited to see these kind of analysis coming more and more because of the computational power, because of the data availability, because of remote sensing information that's available. But of course, one thing to remember, is always to connect the dots. As scientists, you can do, as engineers, you can do, but not everybody, right? So that's where I think your role is very, very critical for climate change related studies. One important thing that I wanted to show you here is we talked about extreme events, particularly for India, monsoon rainfall. Under normal conditions, the ocean heats up, it sends the water vapor. Because of the day and night heating conditions, the motion of the circulation moves into the land, right? We all know that. And then it pours the rain on the land mass. Under warmer conditions, under climate change conditions, you are talking about solar heat producing more heat, or the positive feedback that we talked about, ocean sending more water vapor, Clausius-Clapeyron relationship that I talked about, holding more moisture in the atmosphere, and then that circulation is also getting weaker because of some global effect. We'll talk about global circulation, weaker conditions later, but just keep in mind that if the circulation of the atmospheric moisture is slower and moves to the land at a slower pace, that gathers lots of moisture that's already in the atmosphere. It dumps more rainfall, causing more floods. Whether it's Wayanad floods or whether it is Hyderabad floods or Chennai floods, you are talking about increased moisture with weaker circulation from the ocean front is creating these extreme events. This is directly related to Indian conditions with what we are talking about when it comes to extreme events. Right, very directly applied. Lots of studies are still going on. Why the circulation is weaker? And is there a moisture transport that's happening from the ocean surface? We now know ocean heat content is increasing. Whether it's increasing in Bay of Bengal or whether it's increasing in Arabian Sea or Indian Ocean, how much is it increasing and what kind of water vapor increase are we talking about? What is the circulation pattern are we looking at? How much of increased moisture are we getting onto the land? Lots of questions. Each of them you can ask specifically more and more intriguing questions. And that may come up with new findings. We don't know. For Indian conditions, it might be totally different, right, than what the literature says. So that's an important element to consider for India. Ocean heat content, I think I talked about earlier. Because of this, weaker circulation, India is expected to gain more rainfall. That is the advantage. But if it falls in urban areas, they are always worried about evacuating or sending that water back into the ocean than storing it, right? That's a necessity for safety reasons, public safety and whatnot. But how are we managing the water? Or how are we mismanaging it? That's a different way of asking this. So you can ask these questions again for Indian conditions and see how this variability with respect to monsoon circulation and how it is impacting India. So now this report on a regional scale, they do by state, by region, looking at what happened with respect to rainfall, for instance, in this case. How many days of rainfall, extreme events that north central region or southern region or northwest region had. So the details are here. I mean, in the interest of time, I'm not going to go through that. But this is an interesting graphic I wanted to highlight. These are extreme events, that the same extreme events that I'm talking about, heat wave, cyclone, snowfall, or heavy floods or droughts. So droughts is not here anyway. This is like 365 days, right? These are 365 days. January through February, March through May, June through September. Not even, the remaining months here. Not even 365, I'm sorry, I should take that back. So we are talking about 270 days here. One way or the other, one place or the other, you are seeing one extreme event every day on an Indian scale. If you look at, of course, June through September, more floods. March to May, more heat events that you see. Cold front is in January, February in the north, for example. So these extreme events, that what we are talking about is happening over India. 270 days, but you are seeing extreme events in one way or the other in many regions around the country, right? So this is something revealing for us to worry about. But again, all I am trying to say is this graph, this analysis should be done with high resolution data for every region and understand what kind of mitigation measure we can think about, or I'm sorry, adaptation measure that we can think about. Clearly, humans are impacting climate change, that we are seeing the signatures in 3 of these events: extreme rainfall, heat waves, and cyclones. India has seen the increasing numbers of these events, and we attribute that to activities related to human, anthropogenic changes that we are looking at. Again, winter is very short duration, 59 days only, Jan, Feb in the country. But that's one of the least, fatality producing extreme season. Compared to 92 days of pre-monsoon, heat waves will be a bigger deal there. June through September, 122 days, that they are looking at more heavy rainfall events across the country induced by monsoon, both on the west coast as well as on the east coast, right? But October through December, if you include, it includes the whole country, more floods. That's what you would see. As of today, that we are seeing floods in different parts of India. So the graphic shows that every region is impacted, whether it is Kerala, Tamil Nadu, or Andhra, or Karnataka, or many other places. One, event that what we are talking about, lightning in this case, but then you have heavy rains, including Kerala. If you see in the bottom here, we are talking about heavy rainfall events. Number of days, 64 or 64 days and 56 deaths that we saw in 2023. Likewise, on a country scale, if you look at, extreme events are happening and casualties are also happening. Heat waves are becoming more common. As you can see, Andhra Pradesh, Telangana region, on northeast also, you are seeing more and more of them. So I'm going to actually, leave it to you for reading later on. But climate change is attributed to human activities, and human activities are leading to these extreme events. And we did some work in India through different projects. I think I can cover this up in another lecture. I think I want to stick to the timeline here because we are having the next session in the afternoon with hands-on session on climate model data downscaling. We want to be on time for that. At least we'll start after lunch. But since we started little late today, we got this half an hour extension. Kind of rushed through this literature because when I saw the sense that at least 50% of you had some climate change basics and some of you wanted to know basics, I kind of tried to do a balancing act of introducing the terminologies, but I may not have gone in depth. But that should not stop you talking to me about some questions or clarifications that you may need based on the topics that I covered so far. Don't feel shy. If some of the topics that I rushed through, ask me during the break, I'll be more than happy to discuss with you, right? Or before the class or at the end of the class or whatnot. We can talk about that. Now, it's a quiz time. Are you all ready for that? Yes? Very good. I like that. So we'll go from here. I'm going to skip all of this. I'm not going to talk, or individually I will not come to you, but I'm going to ask you general questions. Sorry, yeah. Okay, tell me this. Which factor is the largest contributor to recent warming? Greenhouse gas. Is that correct? Everybody agrees to that? I want an answer from that side of the classroom now, for the next one. Which extreme event is most clearly increasing globally? All of the above. Very good. Yes, that's the correct answer. It's simple. Water cycle acceleration means what? More snow or higher ET? We didn't talk about ET, but talked about more intense rainfall, faster fluxes, then less evaporation or fewer droughts. What does water cycle exactly mean? So should we go for the second option? Yes, that's correct. Over 90% of excess heat in the climate system is stored in Very good. The last one. Which teleconnection, I did not cover this topic, so I will do justice only after covering this, but I'll still provoke your thoughts on ENSO. Okay, that's good. North Atlantic Oscillation, Arctic Ocean Oscillation, I think the other one is ENSO, and this, South Atlantic meridional oscillation or something. We will come back to all that discussions about metrics here, climate index. But what I wanted to say is all of these topics are kind of connected or related. We will come to teleconnections and what are the important ones for India, maybe tomorrow in the flood class discussions that I will say. But I wanted to kind of keep the pace with our class without getting our schedules disturbed too much. So again, I'm interested in listening to you and getting your feedback on whether or not this is going at the right pace, or should I slow down or increase the pace, whatever you feel. Please convey that to me individually or as a group. I don't mind getting your feedback and modifying the strategy based on that. Okay, I'll stop here. Thank you. We'll see you again in the afternoon. Okay.